Now, finally, beyond just getting satellites around the Earth, perhaps one of the most exciting aspects of space is to be able to send spacecraft that either visit other planets or that might even escape the solar system. One of the things we can ask is, what do we need to send spacecraft to, say, the moon or Mars? There's, I would say, kind of two different approaches to this. One would be sort of brute force, and the other one, you would actually use the force. In the brute force method, that's kind of described here, what you do is you essentially build a rocket. You need to be extremely rich to do this, obviously. And then you can fire an engine on Earth and essentially point in the right direction. The right direction will obviously assume that you took 263 and you know the properties of ellipses, and you've calculated the position at which, say, Moon or Mars will be when you arrive there. So you need to take that into account. But in principle, you could just take a straight shot. The problem is, because there's limited payload due to fuel, fuel is also very expensive. Also, because it's just everything's incredibly expensive, this is rarely done at all, even if you are extremely rich. The method to do this is actually to explore something that is called the Hohmann minimum energy transfer orbit, or to essentially be smart about what you're doing. Instead of just shooting directly, what you can do is you can calculate an orbit that typically involves the sun at one of the focus. So you can use the sun that will attract your spacecraft, for example, to actually go to the position that you require. And depending on whether you're going to inferior planets, those are closer to the sun and the Earth, or for superior planets, your calculations may be slightly different. So as a simple example of, say that you want to send a spacecraft to Mars, and the Earth is here and Mars is around there at launch, you could think, well, it would be much easier to shoot straight away. It is not, because if you do that, you're feeling the pull of the sun. So it is cheaper, actually, if you shoot in the direction where your spacecraft will be orbiting the sun. It will feel its pull and actually meet Mars around here. This will take much longer because Mars will have to have moved a lot and it will take a long time to get there, but it saves you a lot of energy so that you don't have to spend all the money on the fuel and you can do some science. Now, if you actually want to go beyond the orbit of Mars, the way to do it is you calculate an orbit such as this, but actually planning to get at least to Jupiter. And if you just want to visit Jupiter, that's it. But if you want to go even beyond Jupiter, the way to do it is you calculate an orbit up to Jupiter, and then you actually get Jupiter to kind of give you a kick so that you can go further. This is called gravitational slingshot, and this is used for anything. If you want to go to Jupiter or beyond, you always use Hohmann transfer to Jupiter, and then you gain energy off it. And the great thing, as you can see here, is that your maximum final velocity will be equal to your initial velocity of, in this case, is the ball that you can see on the animation. This would be something like taking an orange and hitting it, don't do it, but hitting it against a train at just the right angle so that the ball comes out with the initial velocity plus up to 2 times the velocity of the train. So it allows you to get your orange to move much faster. It would probably be smashed into pieces anyway. But here, you're not really looking into smashing into Jupiter. You want to get close, but not hit the actual planet. And if you want to go to Saturn, this is something you do. So you'd calculate the Hohmann transfer to Jupiter, and then you slingshot off it to get to Saturn. And in principle, you could even then slingshot from Saturn to go to further and further places. And perhaps the most famous, most spectacular example of a slingshot, a successful one, is featured here, just behind me. This was still an artistic impression. It became very real. It's just that we cannot get a picture of this because how far away it is. So you can see that it says it's presently 137 AU, but it's actually more like 150 AU right now. It's the only probe, or more like the only probes, because both Voyager 1 and 2 have now essentially left the solar system, and they're moving at still incredible speeds of over 10 kilometers per second. It's taken them more than 30 years actually to get there, but what they did was essentially taking the smart move of an Hohmann orbit up to Jupiter, and then slingshotting in Jupiter, Saturn, Neptune, all the gas giants until they went into a trajectory out of the solar system. Actually, they are so far away that it now takes almost a day for the information to reach the Earth. So this is it for section 3. I'll leave you with a quick recap of the things that we covered. There's a lot of material that I assume you already knew, and that's why it's still here. And I didn't go through it in a lot of detail. If you have questions or doubts, please just let me know. And what I would encourage you to do is to look at the end of section 3, that's 3.12, where you have a lot of questions with detailed solutions that hopefully will help consolidate your understanding of what we just covered. And once you do that, you will be definitely ready to move to astronomy and to some of the core concepts that can be very weird, but hopefully will be very useful, such as magnitudes, fluxes, and luminosities. So I'll see you for section 4.